Hello, this is Alice J Schmitz's superconductivity in 5 minutes or less. I hope you're ready to get cold because this hot topic works at extremely low temperatures. A superconductor is defined as a material which can conduct electricity with no resistance. The primary limit to this phenomena is temperature, with superconductors only exhibiting this property below a critical temperature. Above this temperature, superconductivity ceases. But how cold is cold? Well, when they could make them work at the temperature of liquid nitrogen, it was revolutionary, so really cold. Hold on to your hats, folks, it's time to get theoretical. So, the one key idea within superconductivity is this thing called the Meissner effect. This is the idea that superconductors can exclude magnetic fields. The field cannot be penetrated by the material, but there's a complication. This is only observed above a critical temperature and a critical magnetic field strength. Superconductors can be divided into two broad classes. Type 1 superconductors, which have one simple field strength above which superconductivity ceases, and Type 2 superconductors, which are far more complicated beasts altogether. Type 2 superconductors have two critical field strengths. Above the first, superconductivity remains, but whirling vortices of magnetic field can penetrate the very surface of the material. Above the second critical field, superconductivity ceases altogether. Now, my dears, it's time for a history lesson. The first superconductors were metallic, primarily mercury-based. Lots of metals are superconductors, the vast majority of which are type 1. 3 type 2 metals exist: vanadium, niobium, and technetium. Alloys also exist, with niobium alloys being key. They're used in NMR magnets and are the magnets of choice for huge-scale operations, such as the Large Hadron Collider. Although niobium alloys have the highest critical temperatures of the metallic superconductors, the LHC uses low temperatures of around minus 273.1 Celsius. That's a fair bit colder than outer space. The group themselves can get up to a balmy minus 253 Celsius, and were even commercially available in 1962. Onward, copper became the star, specifically its oxides. The copper oxide field has a far higher set of critical temperatures than the metallics, and runs via the type 2 mechanism. The copper oxide superconductors can even get up to the toasting temperatures of liquid nitrogen, which makes them far easier to study. Other superconductors include molecular superconductors, based on a compound known as TMTSF. These were discovered in 1979 and are also known as Beschgard salts. They need high pressures to operate, however they have the distinct advantage of being organic, and are therefore made of extremely common building blocks. A slightly better known molecular superconductor is the fullerene, which superconducts when metals are placed between the balls in the lattice. Back to the joys of theory now with some mechanistic grit. If you've still got your hat, I now suggest gluing it down. Type 1s are also known as simple superconductors. They operate via the Barnstein-Cooper-Schrieffer model, also known as the BCS model. This model operates on the notion of formation of correlated but spatially distant pairs of electrons, which move through the lattice of the superconducting material. As the first electron passes through the lattice, it pulls in the nearby molecules of the lattice towards it. Extrapolating this minor compression through the lattice, an equal minor pocket of positive charge is created at some point. This point attracts the second electron of the Cooper pair, which could be seen to be in the electrostatic slipstream of the first electron. The joy continues. We're going there. Meet my old friend quantum mechanics. This combination of two electrons turns them into a boson, which no longer follows the Pauli exclusion principle. Therefore, all of the pairs can be in an identical quantum state, known as a Bose-Einstein condensate. Assuming the energy within the solid is low enough for the electrons not to reach a higher energy quantum state, they will all stay in this ground state, and thereby be unable to interact with the particles in the solid. Therefore, the material has a resistance of 0. And as for type 2 superconductors, the simple answer is that nobody knows. Okay, so thanks for the lecture, Schmitz, but why do I care, I hear you cry? Well, they are in fact really rather handy things, with uses from medicine to transport and right into infrastructure. Medically, they're used for scanning, currently used in MRI, with the potential for MRI-type scanners that don't need huge magnetic fields. They also have macroscopic transport uses due to the potential for levitation, such as in the maglev trains. The most exciting use, though, lies in the ability to transport electrons at no wastage at all. This would have a huge economic and environmental potential. So, thanks for watching. I've been Alice Schmitz, a third year chemistry undergrad. I hope you enjoyed that.